Hello everyone. Before working out with the numericals relating to working stress method and limit state method, we need to first understand the basic concepts relating such. So first of all, we will be studying about the types of steel. There are basically three types of steel that we will be using while designing the problems relating to working stress and limit state method. So the first is Fe 250 steel, which we refer to as mild steel. And the value of Fy for the mild steel is 250 Newton per mm square, and Fy is nothing but the yield strength of the steel. The second one is Fe415 that we refer to as Tor steel, and the value of Fy should be equals to 415 Newton per mm square, that is the yield strength. The third one is Fe500 that we refer to as TMT bar, where TMT stands for thermomechanically treated, and the value of Fy is 500 Newton per mm square, that is the yield strength of TMT bar. The second topic that we will be discussing about the grades of the concrete. There are basically four types of concrete that we will be using while designing the problems relating to working stress method and limit state method. They are basically M15, M20, M25 and M30. So when I'm writing M15, I mean to say that the FCK should be equals to 15 Newton per mm square. FCK means the characteristics strength of the concrete. We can also say that FCK is equals to 15 MPa. Similarly, if I write M20, that means the value of FCK should be equals to 20 Newton per mm square, or I can write it as 20 MPa. In page number 70 of IS 456-2000, we can find the different values of the depth of the neutral axis, varying according to the different grades of the steel. So we can see for the Fy 250, the value of limiting value of the depth of the neutral axis is 0.53. Similarly, for 415 it is 0.48, and for 500 it is 0.46. Let us see in the code. As you can see, this is page number 70 of IS 456-2000, and in this note we can see that the limiting values of the depth of neutral axis for different grades of the steel based on the assumption in 38.1 clause are as follows. And here we can see the different values of limiting value of the depth of neutral axis varying according to the different values of Fy. So the another topic is design method and basis for design. There are basically two design methods. For the first one is working stress method and the second one is limit state method. The limit state method has two states. The first one is limit state of strength and the second one is limit state of serviceability. So what does they mean? Limit state of strength means the state beyond which the structure is not safe for the occupants. Similarly, the limit state of serviceability means the state beyond which the occupants are not comfortable to dwell. Now let us discuss some assumptions relating to the working stress method, and these are all mentioned in the Annex B of page number 80 of IS 456-2000 code. So let us go there. This is page number 80 of IS 456-2000, and here we are able to see the various assumptions relating to the working stress method. As you can see, there are assumptions for the design of the members. That is, the first point says at any cross section, plane section before the bending remains plane after bending. The second point says all tensile stresses are taken up by reinforcement and none by concrete except as otherwise specially permitted. The third point says the stress-strain relationship of steel and concrete under working loads is a straight line. And the fourth point states that the modular ratio M has the value of 280 divided by 3 times of sigma CBC, where sigma CBC is the permissible compressive stress due to bending in concrete in Newton per mm square. So we have written down here the point number D that says the modular ratio M has the value of 280 divided by 3 times of sigma CBC. And its different values are provided in table number 21 of page number 81 of IS 456-2000. So let us see there. So this is table number 21 of page number 81 of IS 456-2000, and what you can see here is the permissible stresses in concrete, and the different values of sigma CBC are provided here for the different grades of the concrete. We can also write that the modular ratio is the nothing but it is the ratio of modulus of elasticity of steel to the modulus of elasticity of concrete. Now the next topic is allowable stress or permissible stress. So what does this mean? So permissible stress means the fraction of characteristic or yield strength that is permitted in a given section. So what does sigma CBC mean? Sigma CBC means the ratio of FCK divided by the factor of safety, where the factor of safety is 3 for the concrete. The second one is sigma ST, where sigma ST means the permissible stress in steel due to tension, and it is the ratio of the Fy divided by the factor of safety, where Fy is the yield strength of the steel, and the factor of safety for the steel is taken as 1.78. Now we will be discussing about the moment of resistance and stress relation. So here I have drawn the section of the beam, and these are all the reinforcement where the area of the reinforcement is AST, and B is the width of the beam, and NA is the neutral axis, where N is the depth of neutral axis, and small d means the effective depth, capital D means the overall depth, C means the compressive stress, CT means the stress on the concrete around steel, where the C acts as 1/3 of the depth of neutral axis, and this is the stress diagram and the strain diagram for the section of the beam that is shown in the figure. So what we can write down here is a stress on the steel should be equals to Young's modulus of elasticity of steel times the strain. So from this we can write ET should be equals to T divided by ES, where T is nothing but sigma ST. Similarly, stress on the concrete around steel, that is CT, means EC into ET, where EC means the modulus of elasticity of concrete, and we can further write down it as EC into T by ES. So CT should be equals to T divided by M, where T means nothing but sigma ST and M means modular ratio. Now we can write as NC is equals to N1 times of D, where NC means the critical depth of the neutral axis, and N1 means M divided by M plus R, where R means the ratio of T by C, where T means sigma ST and C means sigma CBC. Now what we can write is moment of resistance due to the concrete should be equals to C times of Z, where C means the compressive stress and Z means the depth of the lever arm. So we can further write it as C times D into 1/3 of N. And on further simplifying it, we can write B into N into C plus 0 divided by 2 times D minus 1/3 of N, which is the lever arm. So what we can finally write is moment of resistance should be equals to half of BNC times D minus 1/3 of N. So on further simplifying it, as we know, the critical depth of neutral axis should be equals to N1 times of D. So on further simplifying it, I can further write it as 1 by 2 times BD square into N1 into C times 1 minus 1/3 of N1. What I did here is I just simplified it as N1 times of D, and here N as N1 times of D, and I took D as the common here. So now I can write moment of resistance should be equals to QBD square, where Q means half of N1 times of C times 1 minus 1/3 of N1. Similarly, moment of resistance due to the rebar, that should be equals to tensile stress times D minus 1/3 of N. So I can further write it as T times of AST, where T means nothing but the sigma ST times AST, that 2 multiplied by D minus 1/3 of N, where N is the depth of neutral axis. Now we are going to discuss about the types of section. There are basically three types of section. The first one is balanced or critical section, the second one is under reinforced section, and the third one is over reinforced section. So let us discuss about the first topic, that is the balanced or critical section. So if concrete and steel fail simultaneously, then such section are balanced or critical section. That means the maximum stress in steel and RCC reaches at the same time. So what I can write here is moment of resistance should be equals to half of B and C multiplied by D minus 1/3 of N. Or I can write it as moment of resistance should be equals to T into AST times D minus 1/3 of N, where N is nothing but NC and C means nothing but sigma CBC. Similarly, T here means sigma ST. The second one is under reinforced section. So if reinforcement fails before the concrete, then such sections are under reinforced section. And for this, maximum stress in the steel will reach before the concrete. So what I can write here is moment of resistance should be equals to T times of AST multiplied by D minus 1/3 of N. The third one is over reinforced section. So if concrete fails before steel, then such section are over reinforced section, and for this the maximum stress in the concrete reaches before the steel. So the moment of resistance should be equals to half of B and C times D minus 1/3 of N. So what I can finally write down is if the depth of neutral axis is greater than the limiting depth of the neutral axis, then the section is over reinforced section. Similarly, if the depth of the neutral axis is less than the limiting depth of the neutral axis, then the section is under reinforced section. I can further write down it as if N is greater than NC, then the section is over reinforced, and if N is less than NC, then the section is under reinforced. So if someone asks which section would you prefer and why? So if I have to select, then I would select the balanced or critical section. So this is always preferred as concrete and steel fail simultaneously in balanced or critical section, but it is really difficult to obtain such section. Now if I was to compare under reinforced and over reinforced section, then I should select under reinforced section over the over reinforced section. As under reinforced section, we know the steel fails before the concrete. That means the ductile failure occurs here. Whereas in the over reinforced section, the concrete fails before the steel. So in case of the ductile failure, we can clearly see some signs that the occupant may notice the danger and they should rush to the safe place, which is not the case in the over reinforced section. So I would prefer the under reinforced section over the over reinforced section. Now following are the differences between working stress method and the limit state method. So the working stress method is a traditional method, whereas the limit state method, it is a modern method. While designing the beam according to the working stress method, it is found that it is not economical, but limit state method, this is the economical method. Where working stress method is a deterministic approach, the limit state method is a probabilistic approach. The design load is taken as the service load, but in limit state method, the design load is taken as the service load times the partial safety factor for the load. The working stress method is an elastic method, whereas the limit state method is an electroplastic method. The permissible strength of the material is obtained by dividing the yield strength of material by factor of safety in case of working stress method, whereas in case of limit state method, the design strength of the material is obtained by dividing the ultimate stress by partial safety factor. This is all for today. We'll be discussing about some problems relating to the working stress method, and for that you can see the part 1 of the RCC series. Thank you.